This is m1 and this is m2. m1 descends with an acceleration a1 relative to the support, where n1 is the normal contact force exerted by the right inclined plane on the mass m1, and the right inclined plane experiences an equal and opposite reaction force, say r1. The horizontal component of this reaction force, r1x, propels the system to move along the positive x direction, due to which the mass m2 ascends with an acceleration a2 relative to the support, where n2 is the normal contact force exerted by the left inclined plane on the mass m2, and the left inclined plane experiences an equal and opposite reaction force, say r2, and the horizontal component of this reaction force be r2x. As the system is moving towards the positive x direction, we can write the equations of motion for the support to be r1x minus r2x to be some value. If the horizontal component of the normal contact force due to m1 had not been equal to that of m2, the support would gain an infinite amount of acceleration, which is ridiculous. Let's see. Yes? Therefore, n1 is equal to n2. So what we have seen in the simulation, r1x must be equal to r2x. And this is our first equation. These angles are given as alpha, and we choose a reference frame with respect to the ground to be at this point. And we draw an axis perpendicular to the base, and we name it y-axis. Now, as this is alpha, this is also alpha, and this is also alpha. We join these two lines, and as this is alpha, we find this angle to be also alpha. And we claim this angle to be x. So pi by 2 is equal to alpha plus x plus alpha, from which we get x is equal to pi by 2 minus twice alpha. Therefore, this angle is equal to pi by 2 minus twice alpha. So taking pi by 2 minus 2 alpha to be equal to beta, we get this angle to be beta, this angle to be alpha, and this angle to be alpha. This is n1, and this is m1g, this is m2g, and this is n2, where this is mass m1 and this is m2. From the first equation, we have r1x is equal to r2x, and r1x is n1 sine alpha along the horizontal, and r2x is n2 sine alpha along the horizontal. Therefore, n1 is equal to n2. This is a second equation. So in this world, there is no friction, no restitution, and no air resistance. This is the perfect playground to analyze the problem. Mass m1 descends, propelling the system to move forward along the positive x-axis. Mass m2 ascends because of this motion. Now let's look at this in slow-mo. Now let's analyze m2 first. Our intuition says m2 accelerates along the normal with respect to the left inclined plane. We can see that in this simulation, as m2 detaches from the left inclined plane, its motion is along the normal to the left inclined plane. Now let's focus on the mass m1. Pay close attention to my cursor. I'll only move the cursor vertically downwards. And so it is clear that m1 moves vertically downwards with respect to the ground. This is m1 and this is m2. As we have seen in the simulation, the acceleration of mass m1 with respect to the ground is vertically downwards, which is a1g, and the acceleration of mass m2 with respect to the ground is normal to the left inclined plane, which we can write as a2g. Now, for us to find the mass relation, we must first find the direction where the relative displacement would be zero. Therefore, if we connect the bodies, the relative displacement is zero along the normal to the right inclined plane. And if we denote it by n cap, so n cap is the direction where there is no relative displacement. And if there is no relative displacement, then the accelerations a1g and a2g when projected along n cap are equal. So the normal accelerations a1g normal along n cap is equal to a2g along normal. And this is our third equation. This is m1 and this is m2. We have here n1, m1g, m2g, and n2. This angle is pi by 2 minus twice alpha, and this is m1 g cos alpha, as this angle is alpha. Now projecting all the forces along n cap, which is the direction normal to the right inclined plane, we have for m1 n1 minus m1g cos alpha is equal to m1 a1 g n, where n denotes the normal components of the acceleration of mass m1 with respect to the right inclined plane. For m2 we can write m2 sine pi by 2 minus twice alpha minus m2g cos alpha, as this angle is alpha, so this angle is also alpha, and this is m2g cos alpha, which is equal to m2 a2g n. We know from the previous slides that a1gn is equal to a2gn. Therefore, we can write n1 minus m1g cos alpha equal to, divided by m1, n2 cos twice alpha minus m2g cos alpha divided by m2. Now n1 m2 minus m1 m2 g cos alpha is equal to n2 m1 cos twice alpha minus m1 m2 g cos alpha. This and this cancels out, and we are left with n1 m2 is equal to n2 m1 cos twice alpha. N1 is equal to m2, so we get the relation m2 is equal to m1 cos twice alpha. From here we can see that the maximum value that m2 can have is m1 cos twice alpha. Therefore, the relation we are interested in is m2 is less than m1 cos twice alpha. And this is our answer. Thank you for watching.